Welcome students. So now we are going to the topic LCR circuit phasor diagram on resonance. So one by one we just start to explain, like the first one, think AC circuit containing inductance L, capacitance C and resistance R in the series combination. So as you can see, this is the diagram where L is the inductor, R is the resistance and C is the capacitor. So we know that in all these from the potential drops. Because of this, all these are as works as an external opposition sources like a resistance R. So here, if we apply the sinusoidal wave, as you can see, this is a sinusoidal wave. So we need a potential. This is the alternating current source, which is a we can assume as a V is equals to Vm sin omega t and E is equals to E naught sin omega t. The basic difference between these two, here E we are taking as a form of EMF and we are taking as a source voltage. So both we can take, like, because of the inductor we can say, because of the inductor there will be EMF induced. So for that reason we can take E is equals to E naught sin omega t, and otherwise we are just taking the main source, which is the V is equals to Vm sin omega t. What is the Vm showing here? The maximum voltage. Maximum voltage drop. Now, so from starting, as we can say that, let us, we have a alternating source. That means alternating EMF, which is E is equals to E naught sin omega t or V is equals to Vm sin omega t, be applied to a circuit containing inductance L, resistance R and capacitance C connected in series as shown in this diagram. Let I be the circuit in this, like I be the current in the circuit and Q be the charge on the capacitor at any instant of a time. As we can see, this is the current I. We know in this series combination, current will be same everywhere. That's why if we just want to like show this point the current will be, so this will be I. Again at this point the current will be I. Okay, and direction, as you can see, we just take a one direction. The potential difference Q by C across the capacitor and back EMF due to the inductor is L di by dt. So if I'm just talking about the potential for L, the case of a inductor. So for the case of an inductor, this will be L di by dt. This will be V is equals to IR, and for this scenario capacitor, this will be Q by C. All these three, because in the series combination we know there will be a potential difference for each opposition source will be different. For example, if I'm just taking the bulb at R, and different kind of appliances we can take, like if I'm just assuming there will be a refrigerator, so that will be consuming more potential. So like that we can take different types of opposition of a particles, like एक तरफ हम we can use रेफ्रिजरेटर एज आई टोल्ड यू, एक तरफ हम यूज कर सकते हैं बल्ब का, एंड अदर साइड वी कैन यूज एन आयरन. Understood? So these all threes are consuming some voltage, and the voltage drop in the series is the different. Like if I'm just taking the V1, so this is a V1 for this, V2 for this, and V3 for this. Different kind of a potential drop will be there. So for this Q by C, and for this L di by dt. I hope this much have you clear. So this is a complete structural diagram where, as you can see over there, I'll just make in and clear each and every point. For the case of a C, as you can see over there, IXC will be there. In the case of a L, IXL will be there, and in the case of a R, IR will be there. So, hence Vm sin omega t minus L di by dt minus Q by C will be there. Gives the net EMF. This is equals to IR according to the Ohm's law. So, V sin omega t minus L di by dt minus Q by C is equals to IR. After arranging all these terms, we can say that all these three like R, C and L or LCR will be giving the complete main source potential. That means L di by dt plus Q by C and plus IR will be actually nothing but the total voltage which is applied as a source voltage. Current in LCR circuit is given by I is equals to Vm sin omega t plus minus 5 because there will be a potential like a phase difference will be there. And what is the Z over there? Z is the impedance. So where Vm is the peak value of EMF or a peak voltage, where Z is the impedance of a LCR circuit, which is Z is equals to under root R square plus XL minus XC whole square. The case 1, if omega L is greater than 1 by omega C, or we can say that XL is greater than XC. For that scenario, if I'm just taking the current I at any instant in the circuit is given by I is equals to Im sin omega t minus phi, which possible at high frequencies. In this case, current lags EMF by phase difference phi. Case 2. If omega L is less than 1 by omega C. For that case, XL is less than XC. In this case, current I at any instant in the circuit is given by this equation like I is equals to Im sin omega t plus phi. For that scenario, which is possible for low frequency. So one thing which you have to keep in mind, XL is greater than XC is possible for a high frequency student. Okay, and XL less than XC, this is possible for a low frequency reason. In the first case, phase difference minus 5 will be there, and in this case phase difference plus 5 will be there. In this case, current lead the EMF by phase angle phi. From above equation, we can draw the phase diagram, or we can say phasor diagram and vector diagram of a voltage and current in a LCR circuit. So as we can see that this is a diagram for a resistance. This is a diagram for an inductor. And this is a diagram for the case of a capacitor. Clear? Now, if all the threes are mixed up together and making the LCR circuit, for that scenario, what will be happen? We'll just see later. So, if I'll just see like a VL, okay, this is a value of a VL. So, like if this will be the V, so current is actually in the case of a VR is here. VC, like in the case of a resistance, current is lagging, like leading. So for that case, voltage is lagging behind the 90 degree. And in this case, voltage is leading like from 90 degree. So if I'll just take the like vector sum of both, so this will become VL. As we know, like if VL is greater than VC for that scenario, VL minus VC comes in the nature. If Im is the maximum current as given by, so Im is equals to Vm by R square plus omega L minus 1 by omega C whole square to the root. Its impedance Z is given by Z is equals to Vm by Im, where the value of Z is equals to under root R square plus omega L minus 1 by omega C whole square. The current differs in phase from EMF by an angle phi is given by phi is equals to tan inverse omega L minus 1 by omega C into like divided by R. The LCR circuit or LCR series circuit has a very large capacitive reactance XC, which is equals to 1 by omega C. Students, as we know, for a low frequency and for a very large inductive reactance, XL is equals to what? Omega C. And we know that value of XC is equals to what? 1 by omega C. Clear? So this is applicable for a low frequency and XL is equals to omega L. Yeah, this is a beta for what? High frequency. Understood? Again, this capacitive reactance we are using for the low frequency and for the like we are just taking inductive reactance for a very high frequency. Okay, so the particular frequency, the total reactance in the circuit will be the 0. Clear? One will be high, one will be low. So the total will be, if I'm just taking the balancing, that will be 0. Under this condition, impedance Z will be R. So for that case, we can say Z is equals to under root R square plus omega L minus 1 by omega C whole square. And if that omega L is equals to 1 by omega C, that time they both will be factor 0. And Z is equals to under root R square, that will become Z is equals to R. At this frequency, impedance of a series LCR circuit is a minimum and is equals to R, and current is a maximum, that is Im is equals to Vm by R. This frequency is called resonant frequency of LCR circuit, and at that resonance situation omega L minus 1 by omega C is equals to 0. We can say like omega square is equals to 1 by LC, and we can calculate the value of omega, which is equals to 1 by under root of LC. 2 pi f, because we know the value of omega, which is a 2 pi f or 2 pi by t. So this will becomes 1 by under root LC. And frequency value we can calculate, that is a 1 by 2 pi under root LC. This is a resonance circuit diagram. If the current, as you can see, if we just like moving the up direction of with the frequency, there will be a flat thing, as you can see. This is a R1. What is the R1 showing? At the peak, like when the value of a current is less. So that time this flatness will be, as you can see. As much as the current will be high, the sharpness, as you can see. So this sharpness to the flatness is actually showing the diagram between the peak current and the frequency. And by their relation, we can say at this particular point, when we can able to hear the particular sound, like if I'm just taking about the example of a sound, so at the clear sound, the peak will be high. Understood? So this is a for resonance. So the resonance frequency response the curve of LCR circuit as shown in this diagram. It shows the maximum current at the resonant frequency, because like this is the I, as you can see, this is a maximum current. So this is actually resonance situation for that. In the case of LCR circuit, resonance circuit, if XL is equals to XC, then the inductive reactance is equals to the capacitive reactance, or XL minus XC is equals to 0. the reactance of the circuit is 0. So Z is equals to, as we know from the earlier knowledge, under root R square plus XL minus XC whole square is equals to R. The impedance of the circuit is the minimum and is equals to the resistance, which is Im is equals to Vm by R. That is, the current in the circuit is the maximum. This series resonant is called acceptor circuit. This series resonance circuit is called acceptor because why? The reason is that is accept the main current at the resonant position, as you heard from the previous knowledge. This is a maximum. This is a giving the peak value of a current. Okay. This circuit is used in a radio, as I told you like earlier, sound. So in the sound, if the frequency of a sound or the pitch of the sound will be high, we are saying that this is a resonant point. Our TV, radio like this, we receive the desired station by making the frequency of circuit equal to the desired station frequency. Like earlier you did or not a student, but like what we are saying, like at this particular like number or numerical values, the sound of the radio will be, we are just listen a very smooth way, isn't it? Like if I'm just taking the example of like FM. So in the FM you have some number, and that will be depends on the locations. Okay, so if you are just put like 101.9, this is a particular like this kind of a point by which if you just want to connect with that signal or station, so you can connect with that. Understood? So that is the range of frequency which gives the resonance condition, which is this. BW is showing the bandwidth. Okay, at this particular peak, like I will be maximum, that is a condition for the resonance. I'll just go through some questions so that the things will be more clear for you also, students. In the LCR resonant circuit, to increase the resonant frequency, we have these options. L will have to be increased, C will have to be increased, LC will have to be decreased, or LC will have to be increased. The correct answer for this question is LC will have to be decreased. For increase the resonant frequency, LC will have to be decreased. Next question we have, in an LCR circuit, AC circuit at resonance, the current will be is always in the phase with the voltage, always leads the voltage, always lags behind the voltage, may lead or lag behind the voltage. The correct answer is always phase with the voltage. Next question is assertion and reason type. So assertion, in series LCR circuit, the resonance occur at one frequency only. The reason, at resonance, the inductive reactance is equals and opposite to the capacitive reactance. We have these options. Assertion, reason are true, but reason is not the correct explanation or reason for A. Reason is the correct reason of A, okay? And assertion, reason is true, reason is not the correct reason for A. And assertion is true, reason is false, and assertion is the false, reason is true. The correct answer for this question is, student, assertion, reason are true, and reason is the correct reason for A also. So this is all about for today's class, students. I hope you understand the concept, the deep concept of this chapter, like this topic we can say. And if there is any doubt, you just drop your doubts in the chat session. Till that, thank you everyone and take care.